Okay, physics class, so we're going to try a couple of these a week on online notes on an example so we can try to save time in class to do problems with your buddies and teacher present. So hopefully this will be a little more effective than practice. So here's an example called the rotor ride. I'll show you a video, but I googled the rotor ride. So it's this ride that you stand on the outside of this circular thing and they spin you around and go faster. So you're basically sucked to the wall and you keep spinning. Not my cup of tea because I'd be like sick, but here it is. So we're gonna probably don't have to write this whole thing down, and it's coming from your chapter anyway. So 62 kilogram woman and is a passenger on a rotor ride. A drum of the radius 2 meter rotates at a period of 1.7 seconds. When the drum reaches this turning rate, the floor drops away, but the woman does not slide down the wall. Imagine that you're one of the engineers who designed this ride. So imagine that you're riding here and you're standing on this floor, and all of a sudden, whoosh, the floor goes away. Which characteristic would ensure that the woman remains stuck to the wall? So we need to come up with some things. We're going to come up with a force diagram. So here's your force diagram that we're going to say that there's force of gravity, that's that force E. Okay. The normal force in this force of gravity is going straight down. The normal force in this case is actually going to the wall because she's stuck on the wall because there's no floor. Okay. And then the force so we got this. So here's your given. Your mass is 62 kilograms. Your period is 1.7 seconds. And your radius is 2 meters. I didn't mean to capitalize all these, it just was a default. The normal force is perpendicular to the surface. She's leaning on the wall, so if you look at that normal force on this force diagram, it's ND on the wall, is that she's on the wall. Going to the center, that's that radius, the little r is the radius, so if you look at that, it's pointing to the center. And the friction is holding her feet on. So some radial components when we sum this up. Radial means that it's just the x component, but it's radial because it's going to the center. So there is acceleration in that direction because that's the direction that she's changing velocity. So the net force in the radial is equal to mass times acceleration. In this case, the only thing, according back to our force diagram, that is in the radial or x component is the normal force. And recalling that acceleration for radial is velocity squared over r, so I just substituted. So normal force is equal to mass velocity squared divided by radius. The y components, if we looked at it, was the force of friction was going to the top, force of gravity is there, so it's equal to 0, so we can say force of friction is actually equal to the force of gravity in this case because the force of friction is acting up. So we know that force of friction is equal to mu times normal force. I'm going to substitute what I just found for normal force, and normal force was mv squared over r, so I'm just substituting that in. From the above, we said that the force of friction is equal to Fg, which is equal to mg, so I'm going to substitute the mg in there. So for this particular problem, force of friction is equal to force of gravity. So I'm going to just substitute. Looking at the fact that I have mass on both sides and it's being multiplied or divided, I can cancel mass. So you guys, in this case, the mass does not matter. So therefore, mu is equal to g times r divided by v squared. That was my algebra there, so I brought g on the other side with r, divided it to r, and then I wanted to get v squared by itself, so I put v squared, or excuse me, I wanted to get mu by myself, so I exchanged places with those, sorry. So that's algebra. V, if you remember, when you're dealing with period, is 2 pi r over t. So I'm going to substitute that in there for that because I don't know velocity, but I do know period and I do know the radius, so I should be able to figure this out. So substituting in for v squared, I have mu is equal to g times r divided by the 2 pi r over t, and all of that's squared because of the v squared. So when I look at it this way, this is what it's going to look like. Just put the square in there. So force, acceleration of gravity, g, times r, times the period squared, divided by 4 pi squared, times r squared. I can divide out a radius and come up with this equation. G times t squared divided by 4 pi r. Do we know those numbers? Well, we know g. Period was given to us, 1.7 seconds, I believe, divided by 4 pi squared, and the r was given to us. So just substituting in what the problem was. This force of friction, the mu, is going to hold those people in there. So I'm going to take the fact that g is 9.8 meters per second squared times 1.7 seconds squared, that's your period, divided by 4 pi squared times 2 meters. If I'm looking at this whole thing, I'm going to be canceling the the meters and the seconds, so there's no units because the coefficient of friction does not have a unit. So mu, by taking 9.8 times 1.7 squared divided by 4 pi squared divided by 2, is 0.36. So the coefficient of friction to hold the body on there is mu, which is no units, 3.6.